all, and welcome back to Friday. I know I'm one of two more people in between you and a weekend in Las Vegas, so hopefully I'll try and keep things as exciting as I can, but maybe not as exciting as most other entertainment that would happen on a Las Vegas weekend. Because after all, we are talking today about processing Lidar data. A little bit quick about us, so why we're talking about this. Well, for starters, Aerotos, we as a company, we've been doing drone data processing for land surveyors and civil engineers since 2014, which in the land survey world makes us not that old of a company, but in terms of drone-related companies, we are ancient. And so we have done processed tens of thousands of both Lidar and photogrammetry projects, and that's what we're here to share with you. About myself, I'm the CEO and lead photogrammetrist here. I actually come from, academically, I have a statistics background, which is where I learned about all of this. And heck, modern day Lidar analysis and digital photogrammetry is much closer to statistics and computer science than anything else. That's at least why I love it. I know I see some familiar faces. For those of you that were here at my talk yesterday, this is really talk number 2 of a 2-part series that I give about Lidar. Yesterday was all about making use of drone Lidar data, the different Lidar technologies available, their costs, workflows, some basics of processing and that sort of stuff. Whereas today we are going to be taking a much more technical deep dive into all of these systems, workflows, softwares, technologies, methodologies, procedures used for actually processing aerial Lidar data and getting something useful out of it. If you missed the talk yesterday, we actually video recorded it. It is going to be at that link, aerotos.com/westbed22. So if you sign up there, we will send you the video recordings and the PowerPoint slides so you can watch them or share them with anyone else at your office that might make use of them. And the same thing as yesterday, I would love to make this as interactive as a thing as possible. It feels intimidating putting me up on a stage like I'm, a YouTube star or something. But no, I actually really love interacting, and especially with something as new as Lidar technology. Your questions are not only really important to me, they help kind of guide the whole industry. Because while Lidar itself has been around for a while, digital Lidar as it applies to the drone Lidar surveying is still a new and rapidly developing field. Many of the softwares that we use are brand new. Many of the algorithms are changing a ton. I have to, add new slides to the slide deck all the time as we learn new things about Lidar, how it's applicable, and how to get better parts of the workflow. It's exciting making it a rapidly changing part of the surveying industry, which is not super rapidly changing, I should say. So yeah, we are going to be talking all about the processing side of it. So processing Lidar data, which includes photogrammetry integration. As I talked about yesterday, the best Lidar workflows, in our opinions, are those that actually blend photogrammetry and Lidar data together. That's the most optimal workflow to actually get high quality data out of your system. We're going to talk a lot more about point cloud creation, point cloud georeferencing, how do you classify it, what do you classify, what softwares, what algorithms, what settings to use, when AI makes sense and when it doesn't, when you need to go manual. How do you then rasterize all of your Lidar data to turn it from a 2 billion point cloud into a useful raster feature, or vectorizing features and actually creating polylines, tint surfaces, contours, etc. Yes?
Quick question. Do you like the rasterized elevation data better than you like a tint surface?
We're going to talk about it. They both have their purpose, and in fact, in many cases, a single project will have both, and you'll need to be able to convert to and from. So they both have their purpose, particularly. Oh, it's turned on right now. Is it quiet in the back? Okay. I was going to say, I'm a pretty loud talker too. If anyone can't hear me, let me know. I have a microphone and I can make it.
Just making sure you're choosing that.
I'm all good. Appreciate it. But yeah, that's one of the wonderful questions. Raster versus tint surface for surface data. They both have their applications, they both have their uses, they both have their trade-offs. For us, tint surfaces are preferred, a vectorized tint surface is our preferred format, but often to get there you need to use a raster surface as an intermediate. We'll cover that in a lot more detail, but great question. And like yesterday, so these are the things we're going to cover, but like yesterday, I always have this slide up. If your drone program isn't saving time and money, then it isn't working. I am covering all of this not from an academic perspective of how is it possible to create a new algorithm to get something done, I am covering this from a business perspective of how do you integrate this into an actual working survey business. And that means it's not about getting absolutely perfect data, it's about getting good enough data for the project that you have and doing it in a reasonable amount of time. Pretty much everything that you do in business can be done better if you throw enormous amounts of time and money and people and PhDs and scientists and all kinds of stuff out there, right? So a lot of these workflows that I'm going to talk about are what we have found to be the Goldilocks zone workflows to save you time and money. Are there ways where you can individually go and have someone inspect each point in a billion point cloud? Yes, you could do that, and it would take 1 billion hours to do so. Not a good idea from my perspective. So there's so many different ways to approach this. And this is where, again, I'd love your feedback too if you guys are successful with other workflows as well. But from our experience, these are the workflows that provide the best way to save time and money. And so, sorry for those of you that were with me yesterday, I do have a couple of slides that are repeats because really the reason I repeat these is because these are the important principles, right? If you get nothing else out of this, getting these core principles right will lead you to developing your own good workflow. And that's things like making sure that your drone program actually does get you better deliverables. That means that you should be getting the same accuracy as your traditional surveys, and oftentimes better accuracy just from the right point density. If in the past you were doing a vegetated survey, you say this land sucks, I don't want to go through here, so maybe you walk a 50-foot grid. Well, now with a drone you can turn that into a 5 or a 10-foot grid of points, or even tighter than that. That's going to be better accuracy, better deliverables. With a drone, you should always be getting up-to-date, high-quality imagery. You should be able to see everything that is there. That's a huge benefit in a survey that often goes undone or overlooked. That when you deliver a survey with proper up-to-date imagery, it's so easy to look at it and see, oh, we forgot to shoot that, or someone missed that, or something like that. And it's so easy to say, oh, here's why it wasn't missed. You just have a visual record of the site, and a perfect record of those site conditions that you can go back to. These are all parts of getting better deliverables. It should also increase your flexibility. The drone should not be a good working drone system. Should not be seen as something that you have to do and you have to use it and it's a pain in the butt. It should make it more flexible, that you can do new projects. It should serve as a force multiplier. I know I've seen other talks around here about people working with the labor shortages around that it's hard to find people. The drone should be a force multiplier, not something that takes time, it should save you time. And something that you can scale up and down based on your need. That means that if you're doing a 1-acre project or a 1,000-acre project, you should be able to make it happen. And most importantly, again, it should save time and money. That means less manpower in the field without killing yourself in the processing side. And that's obviously what most of this talk is about, because so many people, particularly with Lidar surveys, the field time has become so ridiculously quick. You go out, push go on an autopilot, buzzes and flies, and you've just saved yourself 10 hours. And then you go back into the office and you spend 30 hours on a single project. And that's a really bad trade-off by our estimation. So making sure that you save time and money on both sides is really important. And the way to do that is to avoid many of those surveying pitfalls that are out there. For starters, don't use the wrong tool for the job. This was a funny thing that I was talking about a lot yesterday. If I get one good thing out of this is convincing some people out of using Lidar. Honestly, not good for me from a business perspective, but good for you guys, because Lidar is not the right tool for every job. It's a wonderful technology, but it takes a lot of time and effort. Even excluding all of the hardware, it takes time to process all of it. And it is one tool for the job, so don't use it if you don't have to. And that's a really important thing to be aware of, that it is just one tool, not the only tool that you ought to be using. Also, don't overspend on gear you don't need. Lidar is becoming more and more affordable, but if you are convinced you want to spend $1 million on Lidar, there are plenty of people out there that will sell you $1 million Lidar system. But you don't necessarily need it. Again, I'm really fiercely business-oriented on all of this, not trying to get the best of the best of the best. Don't overspend on gear you don't need. Get the right tool for the job. This is you guys all work probably in work trucks, not work Ferraris for that exact reason. They're very expensive and don't actually do what you need. I focus on the nice, boring trucks. And also, don't spend too much time in the office. In the office, one of the main principles I use is get the data you need, and then get out. It's really easy to spend a lot of time getting more data than you need. Data is a wonderful thing. It's very rich. You can do all of these cool things with it. But you don't want to spend a ton of time getting data that you don't need. Know what you need, get it, and then stop. That sounds super simple, but it's probably the number one thing that we see is people, for starters, they don't figure out what they need in advance. They start working with the data before they've even identified what they're trying to do with it. And then they just kind of keep going, and they classify, and they rasterize, and they vectorize, and create all these cool deliverables that then no one actually cares about. And lastly, don't treat this like a research project. A good drone program is boring, 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 boring. That means you have standardized workflows, documentation, procedures. As much as I love to come up here and like rile people, it's like, yeah, flying robots with lasers, so awesome. No, this is boring. Don't treat it like a research project. The goal is to make this a really good business and make your guys' lives as good as possible. So maybe spending an hour and a half here listening to me talk will save you a couple dozen hours down the line so that you can go and party in Las Vegas. Because at the end of the day, what your clients want almost always is just going to be this. A finished survey. It is a sealed survey. And it doesn't even necessarily say what was taken with a GPS, what was pulled from records, what was taken with a drone photogrammetry, what was taken with Lidar. This project, I know, is a blend of all of those things, and you take the right data, put it together to create the best survey in the best way possible. That's what your job is, and that's what our job is to help you figure out where Lidar makes sense, how to get that data in a useful, practical way, and then how to get on with your lives as well. All right. So, those are the basic principles. Now let's actually dive right into the office workflow itself. As you've seen from yesterday, the standard standard workflow that we go through is 5 major steps. So it starts with mission planning, which we covered yesterday. That's deciding things like flight altitude, overlap, is it a good site even to fly, making that question of LiDAR versus photogrammetry versus nothing at all. That's all on the mission planning side, so if you want that, like I said, shoot me an email, sign up for the video from yesterday. We're not covering that today. Same thing with data collection. That's when you're actually out in the field flying the drone. Covered yesterday, not going to do that too much today. Today, what we are going to be covering in a lot more detail is 3D model processing, line work drafting, and CAD finishing, and actually getting all of this stuff together. 3D model processing being both the photogrammetry process and the LiDAR process, which creates what we call these rich deliverables, your full resolution point clouds, your full resolution ortho photos, that sort of thing. Line work being the actual vectorization of that, creating tin surfaces, drafting your points, polylines, curved lines, gutters, etc. And CAD finishing is then bringing it all together, integrating it with your boundary data, your records research, any other data that you have that wasn't taken from the drone should be blended in CAD to create that final deliverable. And the reason I talk about these workflows, and I have so many of these slides about structures and procedures, is because this is really the most common workflow that we've seen, especially when people are just new to LiDAR. They got this awesome sales rep, maybe they've known the sales rep for decades, they've sold them all this cool equipment. They're like, you need to buy this LiDAR drone, this is the best thing since sliced bread. They spend a whole ton of money on it, they send their crew out into the field with the LiDAR drone, they come back with all of this data, and they're like, all right, see what you can do with it. And that's one of those phrases that always just kind of raises the hair on the back of my neck. See what you can do with it. Because the answer is a ton, and it's going to take a lot of time to do that. And you need to have those goals up in advance, or goals in advance, or else you're just going to spend a ton of time, aiming for nothing and getting nothing out of it. So a better workflow is what gets you better results. So to start with I talk about photogrammetry and LiDAR together, and we'll cover a little bit of both today. An example photogrammetry workflow means that you start with your photos, your ground control data, your RTK and PPK. You process that through your photogrammetry and LiDAR processing system. That creates those rich deliverables. I call them rich deliverables because they're very large files, enormous amounts of detail, more than you need. Things like your ortho photos, your digital surface models, and your point clouds. Typically, these are all what we consider intermediate deliverables, right? That each one of those is going to be many gigabytes in size for bigger projects, and is going to need a lot more work before you can deliver it to a client, before you can even open it in Civil 3D or anything. Then it goes through what we call that line work drafting phase, which is when you actually turn it into vectorized features, your 3D points, Your polylines typically going to be in like a DXF format or one of the more less rich data types. Go through CAD, that's where you actually create your final tin surface. You create your contours based off of that. You integrate all of your other non-drone related data as well that's already there. Add in your site culture, that's everything from labels and symbols and blocks to street names. Typically in like a DWG format, and that's what gets you your final deliverable. And specifically on the LiDAR side of that, the workflow is, this is the workflow that we actually typically use. Now, the best workflows for LiDAR that we found are to use both LiDAR and photogrammetry and blend it together. And that can be done, as I talked a little bit about yesterday, in series or in parallel. Series meaning one after the other, where you start, typically run your photogrammetry first, and then once you're done with the photogrammetry process, then you start working on the LiDAR data. Or depending on the size of your company or what your specialties are, you might have some guy who's a photogrammetry whiz and another person who's a LiDAR wizard, and they both work at the same time before combining everything after the fact. But the main steps for LiDAR processing is, well, you start with collecting the raw data, duh, that part's pretty obvious. Then you go through pre-processing, which is where you integrate the IMU with the raw LiDAR data, sometimes with the photos for colorization, with your GPS and your base station data, and all of your network corrections to actually create your LAS point cloud. Then you've got to align your different flights, your different swaths. You have to geo-reference them. You have to localize them to your project as well to make sure that everything works there. Classifying your point cloud into ground, vegetation, buildings, power lines, power poles, et cetera, and extracting and vectorizing your useful features from there. Now for us, part of the reason these are different blocks is these are very distinct steps. One step needs to be completed before you try and move on to the next step. Especially at the bottom when you're aligning georeferencing, it's possible to really muddy the waters with these, that you kind of start running some classification algorithms before you've aligned everything because you think it's going to save a little time and you want to test it, you want to verify the quality of the data. That's one of those pitfalls that I should point out we really, really don't like, is when you don't have a clearly defined workflow, you might start classifying your point cloud, run some of those automatic routines, and then you georeference it after the fact and you realize two different swaths were off by a foot, and so the ones that was on top was all classified as non-ground and the one on bottom was ground when they should have been aligned and been the same thing. So we really like having these as very discrete steps. In fact, in our data tracking system, like the project can only be in one thing before it gets completed and moved on to the next step. These steps are pretty important for us. As far as what the series workflow example is going to be, well, this is what a standard workflow would look like if you just have one person that handles most of your data processing. We would recommend starting with all of your photogrammetry outputs, your photogrammetry point clouds and ortho photos, extracting as many features as you can from the photogrammetry point cloud first. That's because photogrammetry, as we talked a lot about yesterday, is typically more accurate. Creating your raw LiDAR outputs next, and then once you know the stuff that you can't get from photogrammetry, use the LiDAR data to extract all the parts that were missing from photogrammetry, putting it all into CAD. CAD is where they finally meet each other, those two different data formats, and exporting your final deliverable. Whereas the more parallel workflow, like I said, is going to be having teams do your LiDAR processing and your photogrammetry processing at the same time. But the most important part of this is actually going to be this top step of having good procedures for splitting LiDAR and photogrammetry data so that you are clear that, yes, in vegetated areas, we use the LiDAR data because there is no good photogrammetry model for getting surface data. And with LiDAR, that's where we go and we get all the vegetation. But if it's hardscape, if it's paint striping, if it's roads and curb lines and center lines, then we want to get that out of photogrammetry. Your teams know what you're going to do. So by the time you import it into AutoCAD, it just takes a little bit of QA/QC to make sure that everything lines up nicely. Also, you follow a good enough workflow, make sure that everything ought to be geo-referenced as well, so that your photogrammetry data lines up perfectly with your LiDAR data, which should line up perfectly with all of your field data as well, and your GPS or total station data. So photogrammetry, that step is when you stitch the photos into those rich deliverables, takes a bunch of photos and turns it into a point cloud, ortho photo, digital surface model. I'm kind of going a little bit more into detail of that whole process right now. Your LiDAR processing is when you're then going to classify it into ground, building, vegetation, creating all of that, creating your raster surfaces as well, and eventually into your vector surfaces. And typically, then once you create all those raster surfaces, then you draft your line work. This is how you convert those big raster files into the TIM files, into your vectorized files as well. Partly because raw point clouds, heck, even one classified point cloud, is still going to be way too big to actually be useful in any sort of CAD environment. And then you finish it in CAD. So, final summary, and then we'll go into even more detail, because there is an awful lot of detail. You start with your photos, ground control, RTK, PPK, go through Lidar processing and photogrammetry, create yourself an orthophoto DSM point cloud, create those rich deliverables, those rich, cumbersome, big files that you can't deliver and send. Go through the line work drafting phase. That gets you your lightweight deliverables that are still lacking a little bit of context, points, polylines, throw it all into CAD together. That's when you create your surface, your contours, and all of that stuff. All right. So that is the high-level workflow. Any questions or thoughts on that so far before we get into the specifics? Okay. So let's start with photogrammetry. I know you probably weren't coming here to get a talk on photogrammetry at least, but as I've said a dozen times before at this point, photogrammetry is really important because all of our research has shown that right now, with the current state of technology, photogrammetry, drone photogrammetry can still provide higher quality deliverables than drone-based LiDAR on hardscape. That's the big caveat. LiDAR is much better in vegetation. It has the ability to penetrate vegetation and get you a good ground surface. With LiDAR, photogrammetry on hardscape is better. So that's why I really want to talk about photogrammetry. And again, that's the big thing, that LiDAR is not right for every project. Photogrammetry is better for many projects, and if you don't have a need for LiDAR, don't use it because it's a very complex and expensive workflow. So photogrammetry is the art and science of making measurements from photographs. So that's where it goes from the photos into an orthophoto, point cloud, and a digital surface model. The output is that rich 3D surface model. One of the things to be aware of with photogrammetry is it takes kind of a lot of time. It takes just a little bit of human time. A really skilled photogrammetrist will be able to mark control points, get your datum set up, and throw it into a processing server really quickly. But it takes an awful lot of computer time. For anyone that's done this before using Pix4D, even on a $5,000 computer, your larger projects can take 8 hours or longer for if you're throwing a couple thousand photos at it. And that means that fixing an error and experimenting it can actually take hours because you might try one setting and then you process it, you come back the next day and everything's broken. And improved hardware only does so much. I'll actually be talking about computer hardware as well, because if you're into this sort of technology, odds are you're into the computers that run it too, and exactly what can optimize it. But that comes with the caveat that improved hardware only does so much. Good hardware might be able to cut 10, 20, maybe 30% of the time off of your processing power, but it's not going to turn a 24-hour processing project into a 2-hour processing project. But a good workflow can do that. A good workflow can save you days, whereas spending tens of thousands of dollars on a new computer might save you hours or sometimes even just minutes. So hardware matters, but it should really be secondary to workflow. It's a boring thing to say, but good workflow is going to save you. Investment in workflow and procedures is going to save you so much more time than investment in computer hardware.
Go tell that to our boss.
Especially if they let you play games on it on the weekend and at night too, right? There are a bunch of different ways to process photogrammetry. There are automated cloud-based processors out there. These are going to be your likes of Drone Deploy and Propeller, and I think even Pix4D has some automated cloud options as well. They're affordable, they are fast, they are very scalable, but typically they don't have the accuracy that is required for surveyors. They're very good for a lot of GIS applications where you just need an orthophoto and you can have a couple of feet worth of georeferencing slop. But for surveyors, where especially if you're doing topo and you need your vertical accuracy to be 1/10 of a foot or better, we strongly discourage those. You can locally process it as well, which is going to be owning your own processing machines, Pix4D licenses, that sort of thing. It's highly customizable, gives you the most control, but it's very expensive, both in terms of software, hardware, and your own time, and it takes a long learning curve to actually become a full-blown photogrammetrist. Or you can outsource it to photogrammetrists, which, full spoiler alert, that's what we do as a company, among other things. It's very flexible, no learning curve, and can get you the highest accuracy. The downside is it takes more time often than doing it yourself, and you have to pay for it. Yeah?
Yeah, And also, you can have local processing capabilities, but as more and more people are going out collecting drone data, your local guy might get a little overwhelmed. You can probably do a blend of the two on source there.
That is a great idea, and I'll pay you for the reference after the fact, so thank you. I owe you a drink.
So you just said that investing in your workflow procedures is going to be the greatest spot for efficiency. So how do you recommend we do that? Do you just come down to the company being introspective, or would it be faster to hire a consultant to come help your company?
So step one is you're here. And I'm serious, that's the best thing, is because we're here talking about workflows and talking about software, and I'm gonna help you think about the workflow and procedures as well. That's gonna be step one. And step two is whenever you get a set of data for anything really, and I think this applies not just to Lidar and photogrammetry, but really all aspects of work, don't start by diving in and just getting right into the data and starting processing it. Take a step back and just ask yourself questions like, what is my goal and how am I gonna get there? And it only takes a couple of minutes. A good workflow, that's the other thing. It doesn't take time. It's not like, crazy insanity to create a good workflow. It just takes that ability to step back, almost like step away from your keyboard before you go in. It almost feels like you're being unproductive because you're not getting stuff done. Everyone wants to get in, get done, start working with data, transferring files, processing photogrammetry, keep everything crunching. And if you step away and just think for 5 minutes, it feels almost like you're not getting anything done, and yet that's when you're making the biggest difference there at the beginning. So the best way to have a good workflow is to think about having a good workflow, and that'll get you most of the way there. Another thing, at least for our some of our photogrammetry principles and our workflow about this is, well, number one, work smarter, not harder. Like that, right? Taking 5 minutes at the beginning to think about what you're gonna do keeps you from doing hours and hours and hours that aren't going to be productive work down the line. We also are a really big fan about an iterative process, right? This is a circumstance where, especially when it is internal processing, failure is absolutely okay. You don't have to get everything right the first time. Start with a really quick and dirty model. From a photogrammetric perspective, start with a very low resolution, initial ultra rapid processing just to validate where your photos are there any major georeferencing errors, are there any coverage gaps, are the cameras calibrating at all, did someone leave the lens cap on and things where, you can do that in 5, 10, 15 minutes, and that's going to identify some of those biggest errors before you actually start processing, increasing your resolutions, adding more computational power to it, doing all of that. Go in an iterative process. Also, we are big proponents of having a human in the loop. As technology becomes more and more of a part of our lives, there are more and more automation softwares out there. They are doing wonderful things, and we are huge advocates for automation and advanced technology, but that does not mean that you can have a fully automated process. For anyone that's tried any of the automatic line work, vectorization softwares or AI softwares out there, they're very impressive, but very far from perfect. Especially in a world like survey, where you can't deliver half-assed products and expect your clients to come back. If you say, here's a curve line, and it's 18 jaggedy, disconnected polylines with a couple tenths between them, that's not good enough for a client. It needs to be a nice, smooth curve for an engineer that's going to actually deal with it. And also, we're a big fan of parallel processing as well. This is big for time efficiency too, when you need a big project to go to be finished. Rather than just having one person with one computer take it the whole way down the line, we're a big fan of multiple people, multiple computers. And in fact, wherever you can, split something up, run it across multiple computers, multiple processing servers. And even one of the other things is, with a project that might be challenging, run 4 or 5 or 6 versions of it at the same time. And that saves the human time. Like, you as humans, it saves your time. Because ultimately, your time is, in all likelihood, way more expensive than computer time. Even if you're using very expensive servers, you as people are the most valuable assets to a company, much more expensive than a lot of the server time. That said, I've talked about these computers, and you guys probably like computers as much as I do, so we always like to share what our, at least, computer hardware stack is. This is what our current generation of photogrammetry processing computers use. Now, for anyone that's familiar with this stuff, what you will see is this is effectively a very high-end gaming PC. Normally it would be about $4,000, but nowadays with chip shortages, it's closer to $5,000. But The thing about this is, you'll see that this is a very good computer, but it is not the craziest best computer that money can buy. You can buy your, 48-core Xeon processors or your NVIDIA Quadro processors and things like that. And what we found is that those are just kind of a bad return. When I talk about those principles earlier, those workflow principles, if this isn't enough for you, then buy 2 or 3 or 4 of these rather than trying to buy let me rephrase that. It is better to have 4 $4,000 computers than 1 $16,000 computer. That's kind of our principle. The power is much, much more in these, and you can scale it up, scale it down, do what you need. Granted, you don't need this, especially for smaller companies that are only processing small and medium-sized projects. Even this computer is absolutely overkill, and you can run it on a smaller computer as well. Questions? No other gaming nerds in the crowd that want to geek out about the difference between Ryzen and Intel processors? Okay. I'm sorry, you first. You had your hand up.
So you call it a gaming computer. I much prefer to call it a photo stitching machine, because I always think it's ironic that the way computer people classify a very expensive, high-performance computer is by its least productive use. Because gaming makes you no money, but what we're doing here makes you lots of money.
That is certainly true, but the difference is, if you go to a company that sells gaming computers, they will custom build you this machine for $4,000. If you go to someone that makes professional high-grade engineering workstations, they will build you the exact same machine for $8,000. So that is why I call it gaming machines. Plus, it's just a funny thing, and most of our company is all a bunch of tech people that love this stuff too. So we have all of these. That's actually one of our computers. They're all filled with LED lights, even the ones that are in server closets that no one ever sees. They're just all bedazzled.
Sweet RGB to make sure everyone knows that it's a...
Yeah, and we turn the lights blue to make it extra cold so that they don't know. There was another question.
I was just curious, what component is typically like the choke point on those computers?
Great question. For photogrammetry and Lidar, it's different. I've actually got another slide of this for specifically Lidar processing. For photogrammetry, it's going to be 2 things. One is going to be the CPU. In this case, that's going to be the Ryzen 9 5950X. It's a multi-core processor. Photogrammetry is generally speaking, a CPU-bound process. That's going to be number 1. The video card gets all of the talk and gaming. That's extremely secondary to the CPU processing. Other things that go actually often unnoticed is cooling systems. You get the best CPU in the world, but you don't actually spend a couple $100 to get a good cooler for it. It's going to overheat, throttle itself, and slow itself down, especially when you're doing these long processing things that might take 6, 12, 24 hours or something like that. And number 3 is going to actually be the hard drive. Don't cheap out on your actual solid-state hard drive or anything. It's reading and moving a ton of data, far more than the RAM. We do 64 gigs, but even 128 is still going to get blown away, and it's going to be leaning heavily on the SSD. So those are the ones where, yeah, it seems crazy to spend like an extra $400 on a hard drive and $300 on a big cooler or something. Those are going to be your most bang for your buck, much more so than the graphics card. The graphics card's expensive, and honestly, I would downgrade that for just to save some money if you can too.
But for Lidar graphics,
we'll talk about that in a second, because I got a whole slide for that, and I want to remember everything that I say up there. But yeah, much like photogrammetry, much like everything I'm talking about, it's not about the settings, it's about the workflow. We don't have any sort of magical template that we give to Pix4D, and all of a sudden, ta-da, it processes everything perfectly, and that's how we're good photogrammetrists. So if that's what you were hoping, that I had some secret to make photogrammetry easier, that's not the way it is. So for us, we do manage processing time, and it's worth noting that, like all these things, managing processing time, the computer only does so much. The workflow can help a lot, but much of the processing time is actually decided in the field. That's what I talked about yesterday with mission planning a lot, right? Planning your overlap, planning your flight altitude, that's going to be one of those workflow things that can save you orders of magnitude in terms of time, rather than having a faster computer. Right? If someone goes out in the field and flies at 100 feet and brings you back 2 terabytes worth of imagery, you can buy tons and tons of computers and it'll make it faster, but the best way would be fly at 300 feet instead of 100 feet, and you're going to have 10% of the photos as you would otherwise. that's another one of those things about workflow, right? Take a step back and see what you can do to save time. Sometimes reflying a site that was flown bad is better than spending huge amounts of time processing what you can. So manage your processing time, try and reduce the amount of data that you have. There is such a thing as too much overkill, too much overlap, too much flying too low. Flying crosshatch patterns is unnecessary in order to get good enough data. And also be aware processing time is non-linear. If you double the photos, it typically about 4x's your processing time. So that means the bigger the project, the more time it takes. So just something to be aware of. And like I've said a lot, a good workflow is worth so much more than a good computer. And that is a good field workflow and a good office workflow. We're also big fans of, like I said, staging your processing, running step one, initial processing multiple times, running it rapid and then scaling it up. Having that sort of workflow will help a lot. And also, if you want to learn more about the actual science of photogrammetry, we're big proponents of the ASPRS. We're not affiliated with them in any way. They're a nonprofit organization. They've been founded in 1934 and have been around forever, and they actually do photogrammetry certifications. That's who I am certified with, at least. They actually offer LiDAR certification as well. Yeah?
And what are the requirements of certification? Is it just years you've been working in the industry, or?
It's a combination of things. So they have multiple different tiers of certifications, from a technologist level is kind of their lowest level. And they also have different specialties, all the way from, they have a drone surveying one specifically, to LiDAR surveying, remote sensing, and then certified photogrammetrist is the top tier. It requires 3 to 6 years of work experience, depending on the level, references from other people in the industry, and a written examination as well. So it's actually it's not nearly as intense as actually getting like a land surveying license, but it does actually take time and effort and paperwork, all that stuff. All right, let's keep going into the actual meat of the presentation, which is going to be a lot of the LiDAR processing software itself. So I got a couple different chunks of this, and we're going to start with the actual point cloud creation. Now, this is not the step that many people struggle with, but as I've talked about before, I spent time on it because getting this step right is going to save you time down the line. So we've talked about our LiDAR, this workflow before, just to reiterate it so we're on the same page. You start with collecting the raw data, go through the LiDAR pre-processing, which is going to be creating that point cloud, integrating your GNSS, GPS data, aligning and georeferencing it to the project, classifying your point cloud, extracting your features. And then from there, you import it into CAD and merge it with photogrammetry to create that final deliverable. So, we're done with collecting raw data. I won't go into that anymore, but the LiDAR pre-processing is going to be the next step. So, this is where you go from raw, typically proprietary data into a clean, useful point cloud. Because when the data comes out of the LiDAR sensor itself, purely that LiDAR unit, is just sending a beam back and measuring the distance. And so what it records is the intensity and the distance and the time. And that's it. It's not a point cloud at all, at least from a data architecture. It's just raw data. The problem is that LiDAR sensor is moving around. It's on a gimbal, it's on a moving drone. And it needs to be integrated with the IMU, the inertial measurement unit, to tell it where it is, with GPS to tell it where it is in the real world, in life, and then with the imagery in order to colorize it. And then it needs to be turned into a point cloud that is actually geo-referenced in the proper datum, in NAD83 or NAD22, which now I've heard is delayed till 2025, so that's a future problem I'm not talking about today. The thing with this LiDAR pre-processing is that the exact steps are going to be different for every hardware stack. I'm going to be covering a little bit with what it looks like on the L1, just because the DJI L1 is the most common LiDAR system out there. But typically each LiDAR system will have their own proprietary software. So you kind of have to do this yourself or talk to whoever you bought the LiDAR drone from on the pre-processing step. But that's where, like I said, you take your GNSS and IMU data and you put it all together in DJI. It's a software called DJI Terra to create that actual point cloud. Now, unfortunately, this is typically a very black box software for pretty much all hardware vendors out there, where you throw the data in, it only has a couple of different settings, and a LiDAR system comes out. DJI is extremely black box about this, so that if there are any errors, there's not actually a lot you can do about it. Other software is a little bit better on this step, but more options makes it a little less user-friendly. So that's GNSS IMU processing. Not going to talk about it too much because there isn't that much to do, and it is so individual hardware specific. Aligning your swaths is the next step, and this is where individual swaths of the LiDAR, and in fact, when you have multiple flights or you've picked up and moved to different takeoff locations or moved your base station, the individual LiDAR flights are unlikely to ever line up perfectly. Now, there are some ways around GPS processing to try and get it better in every individual swath and that sort of thing, but be aware that that is not always the case. So you often have to make sure that everything's lined up the right way. And one of the things is just to be aware of that the shifts can come in any direction, not just X, Y, and Z, but they can also be rotated, tilted, and scaled sometimes. So just something to be aware of as you are aligning these swaths, that you want to make sure that you get everything lined up perfectly. To do this, there are a couple ways you can actually line things up. You can rely on post-processes data, IMU. You can get Opus solutions if you have any ground data, or if you have the GPS data for the base station that you used while flying the drone. That's actually our preferred workflow when we fly with the L1. We actually get Opus solutions or similar on the DJI base station to get every single individual flight properly aligned, so that when we pick up our base station, move to a different takeoff location, we can correct it so that those all line up, and we can just get an Opus solution offset from what the initialized position of the GPS was with the corrected position. And that gets everything to line up usually within 1/10 of a foot. Or you can just use node points, check shots. We're big proponents of ground control points and check shots as well. I have more slides on ground control points later for actually verifying accuracy as well. But you can use control individual swaths to ground control points if you have enough control. Yeah?
Are you looking into using the RT or like the triple rovers as a base station for the M300 element on it?
Yeah.
Seeing how that works in that processing?
Works great. It's the very similar process. And in fact, it's a little bit different workflow with how you connect it. And with base stations, I can actually talk about this for a little while. And how much time do I have? Might for a little bit. There are different ways that you can even use your base station, right? When you have, whether you're using Trimble or a DJI base station or anything else, you can set it up over a known point, key in the exact coordinates of that known point, and everything gets corrected on the fly relative to that known point. But you might not always have a known point. You might measure that point, and you need to post-process that, and then come back into the field and then set it up and key it in, and that's a bad workflow itself. So very often what we try and do, and this is back on the workflow side of things, we try and create the most robust workflow out there, which means it doesn't rely on having a known point. If you do, great, use it, but it doesn't rely on it, so that you can actually go up, set up over any point whatsoever. It doesn't even need to be marked. We can say, we joke sometimes, you can even just take your GPS and just stab it into the ground, and as long as it's consistent, we'll just do an Opus there and we'll make it work. And because that's a much more robust solution, and that can be done either with a Trimble or a DJI base station. We try and be very robust with that. So either works, and in fact, much of the data, we can't tell the difference what the base station is. We see a lot of the IMU data and what passes to the drone, and if it comes from a DJI base or a Trimble or Leica or anything, that works. Only reason we like the DJI base station is from a workflow simplicity. It's got like 3 buttons, you turn it on, and it just works. It's kind of crappy for surveying purposes actually, because that's really all it does. I would never use it as an actual survey rover or anything, but for streaming corrections to the drone, it's super user-friendly and idiot-proof.
So, are you saying, so is it logging data as you fly, and then you're post-processing that data to get your coordinates? Is that
Correct. Yep, that's how we work.
And I heard that the PPK, the post-process kinematic, is a little bit more accurate than the real-time kinematic if you're broadcasting corrections. Is that correct, or is that
Yes. So generally speaking, RTK data, the real-time kinematic data, is going to be extraordinarily precise. Precise meaning your relative accuracy, one point measured next to the other. But it's not going to be extremely accurate relative to measuring one point, coming back a month later measuring the same point. It might be off by a little bit. PPK data is what gets you that final accuracy, bringing it down to like global level accuracy. but RTK data is typically going to be very, very, very precise, which is one of the most important things, because our next step is georeferencing. At the early stages, we don't actually care too much about accuracy. In the early stages of processing, we care about precision. And that RTK is very, very precise, especially because when you're using a local base, your baseline distance is so short that the precision is great. And the way that we get accuracy is by georeferencing it to ground control points. Now this is important for a lot of reasons why we think that surveyors really always ought to use ground control points. A lot of hardware vendors out there will say, oh, you can do this, you can do a survey without ground control points. And we actually really hate that, because if nothing else, this is a check on human error, right? If you just have blind faith in the equipment, there's no way to catch any sort of blunders, right? Anything from just you're setting up your base over a known point and you key in the decimal point in the wrong place, there's no way to catch it if you don't have ground control. Likewise, you often have to localize to a project. I'm from California, where things move by 1/10 of a foot every year. And so you actually, most projects are going to be localized to some known point to make sure that all the prior data matches up with all the current data. So one of the simplest, cheapest, easiest, and most reliable ways is to use ground control points. And that means your ground control points to actually make sure that everything else aligns. Ground control points are challenging with uncolorized LiDAR because you can't always see the exact 2D points where it is. You can use features like LiDAR intensity mapping, which is okay. You can use the colorization in a point cloud, which is what one of these is, to try and align it. Sometimes there are some offsets in colorization. There are a couple of different ways to do it. You can actually even, when you process photogrammetry first, you can use your photogrammetry point cloud, if you are confident in it, as a tool to geo-reference your other point cloud and make sure that they align before you start vectorizing all of your features. So there are many ways to align it, but for us this is really important because you want all of your data to align properly. So as I've said, we really like ground control points. They are simple, reliable, they are cheap, they are verifiable, and it goes back to that workflow thing, right? It is technologically possible to do this without using ground control points. But just because it is technologically possible does not mean that it is a good workflow, because it is not reliable. And I like to say that, if you really want it to be done right, hire NASA and have $100 million to spend, because they only have one shot at doing things. They'll take 3 PhDs to double check every single workflow and make sure every setting is right so that you can do it. Or you can shoot a couple control points and get way more accuracy and reliability without needing a couple PhDs to peer review your process. The other reason that we like georeferencing, LiDAR hardware relies very, very heavily on GNSS and IMU, and you also need to use check shots to verify your vertical accuracy. If anyone is interested in ASPR's positional accuracy standards, that's a way of measuring and even certifying your accuracy of LiDAR point clouds. You need to have check shots and ground data to do that. But point clouds, or having ground control points, just provides so much other redundancy in case any other part fails. Yeah, like I said, using colorized point clouds, comparing LiDAR to photogrammetric data, and that blended photogrammetric workflow is all very helpful. So, any questions on georeferencing?
Do you ever use your vertical accuracy checks to move your data up or down if you notice bias? Is that something you would recommend?
Yeah, absolutely.
Okay.
So that's a huge part of it. If we process the data and run everything together and compare it to our check shots and notice that every single check shot or every single control point is 2/10 of a foot lower than the point cloud, then we lower the point cloud to match the ground control point data. And then we typically have independent check shots to verify that data after we do it, right? Anything you control to is no longer an independent check shot.
But like calibration points and then check points.
Correct. Yeah, so in our terminology, it's GCPs, ground control points, and check shots. Those are different things. Check shots aren't used in actually controlling the data. Ground control points are. So having that set, some are used for control, some are used for validation, especially when you do need to properly verify accuracy. And a lot of those can be just anything too, right? Like if you're shooting in utilities, you're just manholes and whatnot, you can use those as a set of check shots easily so that you control your ground control points and just validate the accuracy after the fact by making sure that when it was shot with the drone and the LiDAR, that they come out within your accuracy tolerances. All right, so the next step in creating your point clouds, and one of the big questions, is whether or not to thin your point clouds. I've talked about how there is such a thing as too much data. These LiDAR systems create staggering amounts of data. At least with the DJI L1, it can shoot as many as 480,000 LiDAR points per second. And so it's flying for quite a while too, and with multiple flights, it is not uncommon to have point clouds that are in the multiple billions of points, which is staggering. And this is much like photogrammetry. You could buy your $16,000 computer and it's still going to struggle with a 3 billion point cloud or something like that. So one of the solutions and ideas out there is whether or not to thin a point cloud. This is part of one of those points in the workflow where I'll acknowledge that there's still a lot of debate of what the proper methodology is. Sometimes we do thin point clouds. Usually we try not to, because it can save time, but you also are giving up much of the resolution that you've got. So you want to make sure that you don't lose accuracy. Thinning the point cloud, by the way, there are different methodologies to do it, right? The first methodology is one that we call dumb decimation, which is you basically take a point cloud and you just delete every other point. Or maybe you delete 9 out of 10 points. And that's just, randomly delete points to thin it down, make it smaller. We typically don't like that because you are reducing a lot of your data, and potentially if you fly over a vegetated area and you might only have a couple of points actually on a true ground surface, you don't want to accidentally delete the couple of points that were actually the ones that you really wanted. You want to keep the more important ones, and when you have 1 million points in the tree canopy, you want to thin those more aggressively. So there are methodologies to do 3D thinning, where the more dense the points, it effectively breaks your project up into individual cells. It says if there are 1,000 points in this cell, I'll cut it down to 1, and if there are 2 points in this cell, I'll cut that down to 1. That works as well, but you use a little resolution, it can create some artifacts. It usually can introduce up to 1/10 or 2/10 of a foot of error, even in some cases. So we actually are leaning more and more against thinning the raw point cloud, because we have found that while it does save time, thinning it, especially at the beginning, causes enough data resolution errors and it introduces enough accuracy that we don't like it. The only cases that we actually do thinning, at least in our internal workflow, is after we've classified a point cloud. If someone needs a classified point cloud as a deliverable, we might thin, for example, the vegetated layer, the vegetated class, because trees, you can thin that and you can say, okay, instead of 200 million vegetated points, here's 1 million vegetated points. Brings your point cloud count down a lot, still very reliably tells you where the trees are. Whereas for something like a power line, you wouldn't want to thin that at all because that data is a lot more reliable. Yeah.
And then, if you have I think your point cloud, it does help with the classification, right?
If you thin it?
No. Thinning would be not good for your classification, right? Because you're losing data there. You want
Correct.
data as you want to classify.
Yeah, you're losing data, but the flip side, it does make classifying a lot faster and a lot easier, because classifying 100 million points is a lot easier than classifying 1 billion points. So that's where some of those trade-offs come. And again, I look at those trade-offs so often from that working efficiency side, right? How much are we giving up in terms of accuracy versus how much are we saving in time? And those actually matter, because you could classify each one of those billion points manually. Don't do that. That's a bad use of time.
So in your workflow, do you do the thinning before the classifying? Or
No.
No, you classify them.
Correct. And even then, not always.
Yeah.
So, what software do you use internally to do your automatic region classification?
Great question. So I'll get to that, but internally, our favorite, we actually have some people that work on different softwares. We use for both classification and thinning, we use Global Mapper is probably our primary. TerraScan is kind of our second favorite one out there. And we also have and occasionally use Leica Cyclone and ArcGIS LiDAR module. But TerraScan and Global Mapper are probably our favorites. I think I have a slide on that in this deck too, but generally speaking, we have found there is no magic bullet for this software, just makes everything way easier. These softwares all have fairly long learning curves, so if there's one that you're comfortable with, use it. There isn't a magic software out there that has, just run this routine and ta-da, it perfectly classifies ground. none of
What is
them.
the difference in behavior in the software when you classify terrestrial LiDAR versus photogrammetric point clouds?
So terrestrial LiDAR, aerial LiDAR, and photogrammetric point clouds all have extraordinarily different behavior when you're running a lot of these algorithms and procedures, especially when you have LiDAR with multiple point returns, right, when it's going through vegetation. When everything's pointing down, you can have a very high confidence that the last return is going to be ground. Whereas if you are doing terrestrial LiDAR and it's going from the side, that last return going from vegetation is likely to be the facade of a building. Also, your point densities and point precision is going to be, actually point accuracy, is going to be very, very different terrestrial versus LiDAR versus photogrammetry. Terrestrial LiDAR, because it's so much closer to the subject, and also because it's so much less weight and power constrained, it's typically a much more powerful laser, your actual accuracy is going to be really good. Your curve lines are going to look super duper sharp. Whereas with drone LiDAR, it's further away, it's typically a lower power laser, your curve lines are going to look a lot fuzzier. So any sort of automatic brake line detection tool is going to work way different on a aerial LiDAR versus a terrestrial LiDAR system. So the workflows and I say that because I process primarily aerial LiDAR data, and I know just enough to be dangerous about terrestrial LiDAR data, and enough to know that these workflows, they're different. Some of the principles can probably be applied to ground-based LiDAR, but the exact software and routines probably shouldn't. A great example for that is, this is one of those things that came up, is actually doing error and consistency checking. This should be done very early on in the processes, checking for consistency in LiDAR. LiDAR does create noisy data. There are artifacts from windows can reflect light and in funky ways and create points that are, above the drone. There is noise. There can be gaps in data. The vegetation penetration is extraordinarily impressive, but it's not perfect. You might need to interpolate some gaps. This is another interesting error that we've been researching exactly how to properly mitigate it. This is one where high scan angles can cause erroneous data. What this is, I need to explain it because this is second nature to me, but probably not an intuitive image to a lot of people. This is, at the top, what you are seeing is the LiDAR point cloud classified by scan angle. That means the angle from the drone to the actual ground. The blue line is effectively going to be the flight path of the drone. It flew along there, and blue is where it is pointing directly down. And everything else is the scan angle. The LiDAR is going to be scanning sideways at an angle, so it's a little bit higher. And at the bottom, what we're seeing here is the profile view of that, and of where those two swaths overlap. And you can see that there is a lot of overlap over here. They look pretty tightly put together. But over here, that red data, the high scan angle, is starting to deviate from the other one. This is a phenomenon that we see in other drones and multiple LiDAR systems that seems to be happening in some DJI L1 systems more than others. It's part of actually why we like having a little bit higher overlap that we talked about yesterday. That a little bit higher overlap means that when you see something like this, you can say, oh, we've got high scan angle deviation, and you can just cut anything out with that has a scan angle of above 30 degrees, for example, and that'll get you much more reliable data when that happens. Because the L1, it's a great, like I said, it's not the most accurate LiDAR system in the world. It does have, occasionally has issues like this.
So when you say 30 degrees, that's 30 degrees from nadir, so you have like a 60-degree swap? Is that?
Correct. So yeah, the DJI L1 has a total field of view of just over 70 degrees. So that means its absolute max scan angle is going to be 35 degrees off nadir in both directions.
And then that last 10 degrees on either side is, you're saying?
That last
Five,
5 to 10 degrees, and it depends on it. This is one of those things that we actually are running a lot of testing to see how can we mitigate for it and how can we correct for it. I've said that some software, including DJI Terra, has some really black boxy stuff. They have a checkbox when you're creating the point cloud for optimized point cloud accuracy, if anyone's familiar with that. We've tried using it, and what that occasionally does is it forces these two swaths to line with one another, but it does it in a really dumb way. That it actually, oftentimes, we've done it with a lot of ground truth data and check shots. It'll take the correct data and it'll bring it down to the incorrect data so that it actually gives you bad data. and their documentation on it is atrocious, so we don't actually know what it's doing in the back, but we know that it doesn't produce reliably good results. And then also, early on in this process, before we even start vectorizing, classifying, anything like that, verify your accuracy. I mentioned this before. The ASPRS, that nonprofit organization, has published the ASPRS Positional Accuracy Standards for Geospatial Data, which is the academic backup for this is how you validate and prove the accuracy of your data. Again, this is part of what makes this wonderful is it's based off of decades of research, right? Aerial surveying has been around forever. Drones have just made it cheaper and more accessible that instead of a $2 million plane that only a couple firms in the country might own, hundreds and thousands of surveyors can actually buy these and operate themselves. But the fundamental scientific principles are identical as they've always been. It's just, a lot more computers, a lot more power to make it work. All right, so now we've gone through all of those steps. We have our classified point cloud, we have our georeference point cloud, we verified the accuracy, we've gotten it to control, and what we still have is just a point cloud. We still have no classification yet, we just have 20 gigabytes of junk. Yeah?
Oh, sorry, okay.
No.
Later on, you're going to talk about vertical terrain accuracy checkpoints too?
No, I wasn't, but I can talk about that if you want, right, for a minute.
I mean, yeah, because there is the accuracy of your raw data, the positioning of the drone, and how accurate the lidar is at good distances. But at the end of the day, you're modeling the surface, right? And all models are wrong, but some are useful, and you kind of want to know how useful your model is. So do you incorporate vertical terrain accuracy checkpoints?
Yes, absolutely. And if you really want to read about it, this is this is the gold standard document for measuring that. And in fact, verifying accuracy, what it does, what the accuracy statements on this is, we have tested the accuracy compared to GPS, compared to total station data, compared to whatever, and found the average deviation to be 1400ths of a foot with 95% confidence interval of 1900ths of a foot, something like that. It actually tells you exactly what your accuracy can be.
Can you go through whatever you said right now and explain? I read that and I have a general idea about it. It's like that's really powerful work, what I mean?
Yeah, that's a little hard because accuracy, defining accuracy in a modern standpoint, it's a statistical measure. People want something simple of, what's your accuracy? A tenth. It's like, okay, a tenth of what? And so we typically say that. So I'll give you a little bit, and if this isn't enough, I recommend actually looking through this, because when I say a tenth, what I typically mean is a root mean squared error. And what that means is going to be the, your RMSE is going to be kind of your gold standard. It's replaced all of the national map accuracy standards of the past. But having an RMSE, which is very close to a standard deviation, right? And what that means is it's the average of error across all of your points, but it gives a much heavier weighting to anything that's far off, right? So if you have 9 checkpoints that are all perfect and 1 checkpoint that's a foot off, that's really bad.
That's the problem. When you extend this to the line, you lose it like after 30 seconds.
That's absolutely true, and that's why, and if you actually look at our marketing materials, we say, what accuracy do you get? And we say, typically better than a tenth, a little asterisk. And that asterisk has all of this stuff and a lot of citations. Well, RMSE is not a measure of sigma. So if you were, this is where we're getting dangerously into the world of marketing here, which is not my specialty. I am deeply overeducated in statistics, as I mentioned. That's my background in finance and statistics and why I can talk this stuff. But also, explaining it is really hard, and that's why this exists. This is a 30-page document of explaining what accuracy means. And that's, so I can't go in forever because I could and have actually given 2-hour talks just on these statistical measures of everything, right? Like, it's hard, it's a complex process. And so as far as how to explain that to your clients, it's tough. I can try, but that's why we do often say a tenth of a foot. And then just be ready if there are more questions, explain what a tenth of a foot means to you. For me, a tenth of a foot means, according to an RMSE of better than a tenth, according to the ASPR's positional accuracy standards.
Can you talk about truthing?
Truthing?
Yeah.
Again, you gotta read this. This has some really deep requirements for what sort of checkpoints, how to measure it, what to measure it with, because I don't want to spend too much time. We've only got 25 minutes left, and I know a lot of people do care about the point cloud classifications. And honestly, please do read this. It's very valuable as far as measuring, certifying, setting your checkpoints, ground truthing, all of that stuff. All right, so that said, let's talk about actual point cloud classification. So we were talking about software. It's worth noting most of the screenshots and stuff that we do is going to be taken from Global Mapper. Again, there's no magical software that does everything. That's just what we're talking about. Point cloud classification, as it currently stands, requires a mix of semi-automated and manual classification. This is also a very rapidly advancing field. Many of these software companies are coming out with new and improved algorithms that can better identify different features. They're trying to create automatic vectorization features that are getting better and better and better. And the different softwares, as a consumer and user of the software, it's a delightful battle to watch as they all try and one-up each other, and then this guy created some awesome feature, and so Leica's going to copy it in their software. That's great for us because it makes everything much easier. And it is improving, but the general principles are still that as it gets better and better, it is still quite a ways from requiring no human intervention whatsoever, but it will require less human time as the software advances. So we think it requires a mix, and there's lots of refinement to be seen over the coming years. The first question, though, is not to how to classify the data, but to ask yourself, what classes do you really need? Do you need ground? Typically, that's the most valuable thing. That's the number one thing that people look for. Do you need it to be separated from roads? What about bridges and overpasses when there are multiple ground surfaces, and how do you deal with that? Do you classify low, high, and medium vegetation? Do you need those to be different, or is a single vegetation category work? Do you need buildings separate from everything? Power lines, et cetera, et cetera. Do you need the shield wires to be measured different from the power lines? Different surveys have different requirements. As I said at the beginning, your goal should be to get what you need and get out. For the majority of our LiDAR projects, there are only two classes that we use, ground and not ground. That's it. For the majority of our projects, ground and not ground, and we totally ignore everything else. Because we're there for topo. And that's why we're using the LiDAR data is to create a clean topo. We're not there to model power lines. When we do need to model power lines, that's what we do. Sometimes we do need edges of roads. If you're giving it to a power transmission company and they need to put it in PLS CAD, you need a ton of different classifications. But if you don't need more than ground and not ground, then it's a waste of time and money to start classifying everything else. It's another one of those questions. If you start thinking about the workflow at the beginning, you start thinking about what you need and then only get what you need, that's how you're going to save a ton of time. Here are the different point cloud classification softwares that we use. Like I said, Global Mapper, Carlson Point Cloud, TDC, TerraSolid, Leica and ArcGIS. We have used most of them, and none's perfect. We don't actually have an active recommendation for all of those. The two on the left are the ones that we use most, but the most important is if you're in the ecosystem, if you're familiar with the software, use the one you're familiar with, because the learning curve to actually get up and running with the new software is probably one of the more challenging parts. I did talk about computer hardware. You were asking about computer hardware for LiDAR systems. Generally speaking, LiDAR is not going to be computer bound. It is going to be workflow bound. More expensive computers do not solve many of the challenges with LiDAR. As with photogrammetry, a more efficient workflow is much more valuable than buying a new computer. That said, RAM is going to be important. Having at least 64 gigs of RAM, particularly for large projects. Having a high-speed hard drive, again, is there. Depending on the software you're using, a lot of the LiDAR softwares are actually bound by single-threaded CPU performance as opposed to multi-threaded CPU performance. If you're a computer geek, that means your actual Intel i9 processors are going to be the most powerful. And like before, your GPU is actually rarely the processing bottleneck just due to the computer architecture here. So again, 64 gigs of RAM and your high-speed hard drive is going to be important, but a good workflow can run on nearly any computer. With photogrammetry, just so you guys are aware of how we think of it, photogrammetry, we run exclusively on high-powered desktops. For our LiDAR processing and our LiDAR techs, we use gaming laptops. They're laptops. They're not nearly as powerful as our desktops because that's not really the bottleneck like it is in photogrammetry. Photogrammetry is much, much, much harder on computers than LiDAR. buying really high-end computers isn't really going to fix major LiDAR problems. All right, so let's talk a little bit more about classifying. Classifying ground is going to be almost always the most important thing. That's what we want to. That's what we care about. Usually, when you're running LiDAR, it's because you're going to be running topo. So what you care about is the ground. This is a fascinating one because this is what some of the automated classification routines pulled out. Here's your ground. These ones in orange are going to be buildings, which they're clearly not, to a human at least. Those are clearly in vegetation, blah, blah, blah. But also you gotta be aware there's still some gaps. So let's talk about actually identifying ground surface. And one of the weird questions that you have to ask with this is, what is ground? These automatic classification routines try and find a ground surface. And in many, 95% of circumstances, what is ground versus what is an object is pretty clear. But there are a lot of edge cases. I mean a lot of edge cases, starting with a debris pile. Say you had that big pile of concrete. Would you call that ground? It's kind of a judgment call, right? In some cases you do want it to be ground. In other cases, no, that's trash. You exclude that as debris and you get the surface underneath. But that's, rock and rubble. Maybe that's what you actually care about is calculating that surface or something like that. That's a judgment call and there's no right or wrong answer to it. Same thing with a stockpile. Is the stockpile itself ground, or is that going to be a separate object and you care about the ground underneath, and then you measure the volume of the stockpile as its own different classification? Once again, that's a judgment call. It really depends on the type of survey that you're doing. Same thing with things like rock outcroppings, that, is that an object or is that actually part of the ground? Now, imagine all of these were under trees and you couldn't actually see it whatsoever. All you can see is the LiDAR outline of something, and it's under trees and you see a hump. What is that? Is that ground? Is that a rock outcropping? Is it a debris pile that we should call a piece of the ground? Or is it a car that someone parked there and shouldn't be considered part of the ground and it's an object? These are the type of things that automatic classification routines have a really, really hard time discerning between, because they don't actually see what it is. They don't have the context. Even the most advanced AIs in machine learning and point cloud methodology don't have the context to be able to know, oh yeah, clearly that's someone abandoned a car underneath the forest and that's what that is, so I'm going to exclude it as part of the ground. Those are hard judgment calls to make, and this is part of why a lot of these automated routines, they still require human judgment, and they still require a good amount of work to be able to identify what is ground. And this is just one class, right? This is just what is ground, what should be the simplest thing. But when you're not there on the ground, you can't see what's under the trees. You can only see the elevation data from the point cloud, and that does require some judgment of knowing the site conditions, what's there. Is it by a junkyard and there's a bunch of junk that you want to exclude? Or is it a, pretty much virgin land and you can say, okay, if there's something there, that's got to be a land feature. I don't know what it is, but I'm calling it ground. So all of that is pretty important. Automatic ground classification has a whole bunch of different inputs as well, as far as what your expected terrain slope is. What deviation from that terrain slope will you call ground versus non-ground? How awkward of a shape does it have to be before you say, that's definitely not ground, right? And then there are a lot of different filters in there, from what's your expected terrain slope, and then how long does it have to deviate from that slope for you to call it non-ground points anymore. Stockpiles are a particularly weird one because they show up as a cone, and that cone, whether it's ground, it's like a 45-degree angle of a stockpile cone. The software says that's way too steep to be natural ground, so it kind of excludes it. Because likewise, if you see a car oftentimes is not too dissimilar from, just a mound, and it sees that and says, oh, it's a car, that's definitely not ground. You and I can look at it and say, that's a car. The computers have a lot more trouble from an AI perspective or any sort of automatic classification routine of determining a car from a stockpile. One needs to be included, your stockpile does, your car needs to be excluded. That's a real challenge, and that's where tweaking everything to the right site conditions is important. This one is just an example of two different settings that you can have to allow for some steeper terrain. That one doesn't like the steeper terrain, that one does.
Same piece of software produce both of those, just with different
with different settings. And that's what it is. And there's no, like before, like photogrammetry, there's no magical setting that works on all sites. We spent a stupid amount of time trying to discover with our Lidar teams, we were doing this, what are the optimal settings? And it was a big, like, almost aha moment for us when we realized, well, duh, I teach this type of stuff. There isn't one set of settings. How did I not figure that out earlier? It's about finding the right settings and having these procedures to say, oh, okay, so we're working in a mountainous area of Hawaii. It was actually a Hawaiian project that I did in the middle of December and made me really depressed because I wanted to travel to Hawaii. But that made us realize this because it was this steep hill with a road running through it with all of these crazy jagged rock outcroppings that were natural ground, and we had this software settings that we thought were these magical settings, and it was taking all of this ground and throwing it out, saying, nope, that's way too sharp of a feature, that's not natural ground, it can't change like that, and it was causing all kinds of problems. And then we switch it the other way, and it's like, okay, so these really sharp features, that's ground. And so it would take these trees and say, like, all right, that tree is ground now. And we're like, context here. So it took a while to get those settings dialed in, and it was very, very different on that site than to something that is mostly flat with maybe only 5 or 10 feet of true ground elevation change and 100-foot trees. Those will have a way different set of parameters. So realizing, like Pix4D, like software, it's not about the settings, it's about the workflow. It's about the procedures, that's how you get it. There is no magic set of settings that we've found. There is no AI that is reliable about that. There is nothing that can see underneath the trees and say, that's a car, that's a stockpile. That counts, that doesn't. And sometimes you don't know for sure, and it takes a human judgment to mark it as unidentified object on a CAD template, right? Mark it and say, there's something here, I don't know what it is. That's oftentimes just as important. Grass, shrubs, low vegetation, those require some of their own parameters as well too. As I've mentioned, a point cloud is a cloud. It is not a perfect set of points. So being able to say, okay, here's your statistical average of what we see, it typically has a spread of about 1 foot on hardscape. That means anything over 1 foot, we are going to classify as grass, and that's what it looks like here. This would be a low vegetated area that all of this stuff would be called the ground, and all of this would be called the grass. Once again, trying to optimize that. And then buildings, power lines, all of that. Number one thing is ask yourself, is it worth the time? Automatic classification algorithms have a lot of false positives. We do start with automatic classification, but again, focus on ground, that's gonna be the most important. All right, once again, I'm running out of time, so we'll go to the last step in LiDAR processing now, which is creating raster data. So first off, what is raster data? Raster data is a matrix of cells or pixels organized into rows and columns. Basically, it's pixel data as opposed to vector data, which is going to be points and polylines typically. So why do I want, LiDAR data is by itself vector data. LiDAR data, or vector data is LiDAR data, topo points, break lines, tin surfaces, contours, that sort of thing. Raster data is going to be your ortho photos and your DEMs and DSMs. So if we're starting with LiDAR that's vector data and we want to get to a tin surface which is vector data, why would I input a step of creating it into raster data? And that is a valid question. And the answer is, it's not a necessary part of the LiDAR workflow, but we have found that creating a step that creates raster data from your raw point cloud makes it much easier to work with, and it can help smooth out much of the noise from your individual points. So here's a great example of a surface with some light vegetation. Here's the raw classified point cloud. You have your ground point data, which is kind of noisy here. This is going to be your vegetation. This is going to be a profile of a surface. It actually could be, this one is of a highly precise tin surface where it's taking most of these points and making a tin out of it. And what you can see is it actually creates a lot of really jagged, ugly surfaces. Whereas if you rasterize it and actually have like a 1 foot bin size, what this one actually does is it effectively smooths it into 1 foot bins and takes the mean of all of the hundreds of points within each individual bin, it actually smooths it out. And our analysis after the fact has actually shown that this is a statistically more accurate surface than the noisy one is.
Interesting, that is exactly what we do with hydro data.
Is it really?
Yeah.
Yep. doesn't surprise me at all, right? This is ultimately,
Validation for your process.
well, thank you. So yeah, we find that rasterizing it and smoothing it and taking the average has statistically provided better results than trying to take a really precise, every single point being true, that sort of thing. As I've mentioned, point clouds are not a perfect set of points, they are a cloud, and taking the average makes it better. So the workflow that we use to go from a point cloud to an actual CAD tin, you start with your point cloud, creating a raster grid. Resolution and bin size, we typically like about 1 foot for each individual pixel. And with, we find mean or median, depending on the individual sensor, both work. We don't like using minimum because of what I've said about them being clouds. Converting that then to individual points and polylines, using basically extracting topo points from that grid, simplifying it down in the Lidar or in the line work drafting process, and potentially adding in break lines, things like this. You would have a break line, you would draw break lines along the creek bed and probably do a grid of points and maybe a low pass filter along some of the rest of this to get a topo points, get a tin surface out of that. Get those points and polylines to a tin surface and then add your contours to that. That is what our workflow typically looks like for actually going from the Lidar, the classified Lidar data into the tin surface and contours on the topo side of things. For line work drafting, since we are running out of time, shoot me an email. I have talked about that in depth at other presentations as well, because the line work drafting is the step of just going through and extracting the data that you need. These are your different softwares. It's tedious, like with other things. There are automation tools that help, but are not the magic bullet. And line work drafting does take an awful lot of time. So again, shameless plug, this is the type of stuff that we do as a company. If you don't want to sit there and draw topo points and break lines for hours and hours in a row, we do. And then putting it all together into CAD, merging it, and getting your final survey deliverable. So once again, we are now wrapping up, and so I won't hold you guys away from the happy hour any longer. And once again, if you want a recording of this, then please sign up at lsaw22, aerotos.com/lsaw22, or you can shoot me an email with any questions you have. My email is logan@aerotos.com. So, thank you again on a Friday afternoon for the questions, the interaction, all of that. I truly appreciate it. I appreciate your attendance and sticking with me. Thank you.